time, they've absorbed the ultraviolet radiation, and hopefully what you'll find is you've got some really beautiful white crystals in your tube. So those would be the 7A product that you're going to characterize today. The other thing you're going to do today is you're going to start the 7B experiment. So what we need to do now is talk a little bit about what is going on with all of this stuff. All right. So, but before I forget, on Wednesday we're still going to be in experiment 7. You'll be characterizing 7B at that point, and then you'll also have your experiment 7 lab quiz here. Okay. So let's go ahead and talk about what is going on with this reaction. So in 7A, what you did last time was you took benzophenone, which looks like that, and I'm just going to start abbreviating these benzene rings as pHs just because it's a lot easier that way. So what we did was we took, dissolved this in isopropanol, and then over the last week and a half or so, these guys were absorbing sunlight. And sunlight is obviously ultraviolet light, somewhere in the 350-ish nanometer range. And so as we discussed, kind of the fundamentals of UV spectroscopy is that ultraviolet light can cause electronic excitation, right? You can cause, if you have an appropriate wavelength of light, you can cause an electron to jump, right? Go from, for instance, a pi to pi star orbital. And so that's what we're doing here. The ultraviolet light from the sun is going to cause the electrons of the pi bond to kind of do this, right? And so if you imagine what the result of that is, the result of that is this kind of unpaired electron situation. So you could kind of, a simplified way of looking at it is thinking about now, upon excitation, is you have a situation that looks kind of like that, right? All I'm doing is representing this type of situation where we have two unpaired electrons as a result of one of the electron pairs being promoted into the pi star orbital, okay? So what can happen here in a protic solvent is you can have a reaction. And this is just going to be a radical process. I'm not going to worry about the rest of what happens with this solvent because it's not terribly relevant. But once you protonate, you make a species like that, and then two of these guys can come together. And that makes this structure, which is called benzopinacol. And that is what should have precipitated from the solution, and that's what's giving you those nice pretty white crystals. Okay? What you're going to do today is you need to isolate this. So the way you're going to isolate this is simply through vacuum filtration. So you'll just set up the vacuum filtration apparatus, get your Buchner funnel, and then dump this into the Buchner funnel. And you can rinse this with a little isopropanol if you need to. If there's some residual crystals, you can get them out that way. What I would recommend you do is throw those in the oven for a few minutes. Remember, they're coming directly out of isopropanol, so you don't want to really characterize that wet because you're going to end up seeing a bunch of OH stuff contaminating. So go ahead and once you do the filtration, put it in the oven for a little bit, and if you want to, you can go ahead and get your experiment for 7B kind of set up then. Set up your reflux apparatus and do all that while you're waiting on your crystals to dry. Okay. The other thing you can do is, let these dry for, I don't know, 10, 15 minutes or something like that. Once you take them out of the oven, you can go ahead and get the 7B reaction set up. And that has I believe it's about a half an hour reflux. In the meantime, while you're doing the reflux, that's when you can go ahead and do the characterization of your 7A product. So just some kind of tips to maximize your efficiency here. So what you're going to be doing in 7B, actually before I do that, when you're characterizing, you're going to characterize use melting point, IR, and UV. So in terms of the UV spectroscopy, you're going to do this the exact same way you did for experiments 1 and 2. So you're going to need to calculate the mass of benzopinacol you need to make 10 mils of a 10 to the negative third molar solution. Okay, and then you're going to do serial dilutions from that. So in the same way with experiment 1 and 2, you ended up with 3 concentrations of UV sample, a 10 to the negative third, 10 to the negative 4, 10 to the negative 5 molar. You want to do the same thing here. Right? So ultimately, you should be going into the UV room with your 3 centrifuge tubes. Again, negative third, negative 4, negative 5 molar solutions. And you'll run them in series. Okay. Okay, so for 7B, what you're going to do is you're going to take the benzopinacol and you're going to subject it to a really famous rearrangement that's known as the pinacol rearrangement. And the way you're going to set this up is you're going to use acetic acid as solvent, and you're going to add a catalytic amount of iodine to it. I'm going to show you kind of the traditional mechanism of this. The classic mechanism of the pinacol rearrangement does not include iodine. We just found that with this reaction it works a little better with the addition of it. Don't worry about it in terms of the mechanism. I just want you to know the kind of classic pinacol mechanism, right? But what happens in the classic mechanism here is you end up using strong acid catalyst, and the alcohol is just going to go and grab the proton. So what have we done by protonating the alcohol here?
Made it a leaving group.
Yeah, made it a good leaving group. And so it's going to leave. And do you see why that might be so favorable? Why it would be so favorable to have that leaving group leave like that? How do you like that carbocation? Yeah, this is among the best carbocation situation you could ever imagine. Okay, it's tertiary, right? It's got 3 different carbon groups on it. But even better than that, it's benzylic. And even better than that, it's actually doubly benzylic. So that is a highly, highly stabilized carbocation. Right? And so this kind of leaving group leaving, generating the carbocation, kind of like we see in SN1 and E1 mechanisms, is very, very favorable. From here, this is where the rearrangement occurs. So what's going to happen is we are going to actually reform a carbonyl here. But we cannot simply make a carbon-oxygen double bond without having anything else occur. Because then you'd have a carbon with 5 bonds. So what ends up happening is one of these benzene rings is actually going to shift over. We're going to see some examples of this kind of later. I mean, you've seen examples of hydride shifts and of methyl shifts. It turns out these benzene rings also have what's known as a high migratory aptitude. They tend to shift around a lot. But when that happens, you end up getting this, where as soon as we lose the proton from here, regenerating the acid catalyst, we get to this compound, which is benzopinacol. So that is the reaction you're going to be running today. And it's fairly quick. You know, you'll reflux it for about a half an hour and then it should be good. A couple more logistical things. In your lab manual, it says to use a small crystal of iodine. And I know that's very precise wording. But the goal is you want to have as small of amount of iodine as possible. Okay? The more iodine you use here, the more you're going to have to get rid of in the end. All right, so you try to use a very, very small amount of iodine. The other thing is at the end of the reflux, you're going to pull the round bottom flask out of the heat, let it cool to room temperature, and then you're going to add ethanol to the round bottom flask. And the point of the ethanol there is that it should cause the benzopinacol to precipitate. Okay, so once you add the ethanol, you should see everything kind of get kind of a milky type consistency as that solid precipitates out of solution. And then you'll simply do a vacuum filtration to isolate the benzopinacol product. Okay? And depending on how much iodine you use in the beginning, you may end up with a slightly different color product. So if you end up using a lot of iodine, your product could end up kind of pink to red to brown, just depending on how much iodine you use. It should be white. Okay? So if you end up with a slightly colored solid in the end, just get some cold ethanol and rinse the solid. Just try to rinse away that excess iodine. But the best way of not having to do that is to make sure you're using a small amount at the beginning. Okay? Any questions on this?
How do you know that you've got enough iodine in there?
As long as your solution is colored, you'll have enough. And again, depending on how much you use, it's gonna change the color. You know, your solution could be anything from a pale yellowish brown to a deep burgundy, almost black, just depending on how much you use. But try to use as small of an amount as possible. There's almost not such a thing as using too little. Okay. Okay, so I think that is about it. What I would like for you to get through today is through the isolation of the benzopinacol. You're probably not going to be able to characterize any of that today, but that's okay. We have Wednesday to characterize the 7B product. But what I would recommend you try to do is while your 7B is running, you have a good half hour where you're not going to be doing anything. So try to do the characterization of 7A in that reflux time. Okay? All right. If nobody has any questions, then you can go ahead and get started. The Pyrex tubes are up here. You can grab those, and I'll set some iodine out by the balance.